Well, I know you've been waiting for it, and finally it's here. Two-dimensional motion, and more specifically, projectile motion. It's time to talk about it, because out there in the real world, things move more than in a straight line. What we're talking about here is an object that's moving under the influence of gravity alone. Now, that doesn't mean it's not moving horizontally. For example, a ball rolling off of a table or a baseball being thrown into the air. Most of the time, we're going to be ignoring air resistance because that just makes these problems really much more difficult. And we are introductory physics after all. But when we talk about a projectile, that's the kind of thing we're talking about. In the y direction, which we'll define as up and down, it's going to be accelerating because of the effects of gravity, and it's going to be accelerating at that rate right there. But in the x direction, since there is no sideways gravity, there won't be any acceleration, which means we're going to be working out the problem in the x direction differently from how we work it out in the y direction. And the reason we can do that is because motions in the horizontal and vertical directions are independent of each other. They're perpendicular motions, and all this means is an acceleration in the vertical direction has no effect at all on motion in the horizontal direction. Let me show you what I mean. This video comes to us thanks to the physics lab at the Massachusetts Institute of Technology. Over here on the left, you see a professor with a gun that fires golf balls. And over here on the right, you see a monkey. Okay, it's not a real monkey, it's a toy monkey, hanging up on top of a tower. This gun, if you track it along here, is aimed straight at the monkey. What's going to happen is the professor is going to fire the gun, launching the golf ball. At the same time, the monkey will be released and be falling straight down. What will happen? Well, let's take a look. That was neat. Let's look at it again. Do you see the path of the ball? Pretty amazing, isn't it? Oh, sorry about that last one. What was happening there is that the monkey was falling, accelerating at 9.8 meters per second squared down, and so was the golf ball. The difference between the two is that the golf ball had some initial upwards velocity, so it started moving up, but eventually was coming down. And, this is very important, the golf ball was moving horizontally, but the monkey was not. But the horizontal motion didn't affect the fact that one would hit the other. It was always tracking along with the monkey. It would have hit it as long as they're released at the same time. That's what we mean when we're saying that those two motions are independent of each other. Let's take a look at what this means by doing an example. A ball rolled off a 1.23 meter tall table, that's about 4 feet, at 25.3 meters per second. How far from the base of the table did it strike the floor, and at what speed? Well, if you watch the path of the golf ball in the video, you notice that it followed an arcing path, and that's what's going to happen here with the ball as it rolls off the table. So there's our ball on the table. I chose a softball, and let's suppose it has an initial velocity in that direction. Once it comes off of the table, it's going to start falling, but it's not going to stop moving horizontally because there's no horizontal acceleration, even negative acceleration, to slow it down. Thus, if we put in some little markings here to indicate what's going to happen, we'll see that the ball initially is going to come off the table moving horizontally, but then it's going to start arcing more and more toward the floor. Notice it's still moving horizontally, but it's moving faster and faster vertically. When it hits the floor, it's not moving vertically. It still has a horizontal component, but now it has a big vertical component as well. Okay, it's doing both. Whereas initially it only had a horizontal component. So it was a horizontal and a little bit of vertical, then another horizontal and more vertical, then another horizontal and a lot more vertical, and so on. So that's basically the path that the ball follows. And that's what we're going to try to analyze. Let's call our axes x and y as per usual. And we'll call this distance that it travels horizontally delta x, the displacement in the horizontal direction. And we'll call this delta y the displacement in the vertical direction. And then let's see if we can list some information up here. Remember listing your variables? But unlike anything we've done in the past, we're going to list them in two columns. We're we're going to have an X column and a Y column. Now we haven't done that for physics problems. We did that for vector problems when we were learning the basic math of it, but that's going to come in important right now. And so our velocity in the X direction is given in the problem. It's 25.3 meters per second. Our displacement in the X direction is what we're trying to figure out, so we'll call that delta X. And we'll put a little question mark past it. Now, since it's moving at constant velocity, the equation we're going to be using is the basic one you learned in Algebra 1 class, distance equals rate times time. In physics, we learned it a little bit differently. We learned it as velocity, in this case in the X direction, is going to be displacement divided by time. There are only 3 variables involved because there is no acceleration, but we don't know 2 of them. We don't know the displacement, we don't know the time. That's a problem until we get over to the Y direction. In the Y direction, what kinds of things do we know? Well, we know the displacement. Can you tell me what it is? Well, no, of course you can't. I'm on a video. But can you tell yourself what it is? Well, the table right here is 1.23 meters high, which means the displacement of the ball is going to be negative 1.23 meters. Why negative? That's right, because it's falling, and we chose up as the positive Y direction right there. It also has acceleration. It's not told in the problem, but we know that it has acceleration in the Y direction of negative 9.80 meters per second squared. Now don't forget, if this is done in British units, we would have it as negative 32.2 feet per second squared. That's okay. What else do we know? Well, we know that initially the ball is moving horizontally. So that means its initial y velocity, we'll call that v sub y I for v sub y initial. Sometimes it's called v sub y naught or 0. Means the same thing. In this case it's 0 because it's moving horizontally. If it were not initially moving horizontally, as you'll see in the next problem, then we would have to have a number here that isn't 0. And finally, well, there are 4 things here. What else do we need to know? Well, we don't know how much time it took. So let's call the time the question here. Now I realize that the time is not the question in the initial problem, but the key is this. If I can figure out the time over here, then that means I can figure out the time over here, that along with the velocity, and we can get that displacement. We can also eventually figure out the speed. So let's take a look at that. What equation relates these 4 variables? That's right. It's displacement equals initial velocity times time plus 1/2 acceleration times time squared. Okay, we learned that back when we were first doing kinematics. Let's plug in the numbers. Negative 1.23 equals, well, this is kind of nice. The initial y velocity is 0, so I can just put a big fat 0 there. Plus 1/2 times negative 9.8, that's minus 4.9 t squared. And when we solve that, we get that t is equal to 0.501 seconds. Here's the key to the problem. Although the movement in the horizontal direction and the movement in the vertical direction are independent of each other, there is one thing that links them together. They were happening at the same, what's the word? Time. They were happening at the same time. So that means the time in the y column and the time in the x column, they're the same. So I can put that over here. And now we can work the problem by writing 25.3 equals delta x over 0.501, or in other words, the displacement in the x direction is 12.7 meters. Now, if you're thinking that's an awful lot, 45 feet or so, you're right, but this ball was rolling really, really fast. 25.3 meters per second is hustling along at a pretty nice speed. That's about 80 feet per second, so maybe around 50 or 60 miles an hour. That ball was really hustling off that table, and so it traveled quite some distance before it landed. So we've answered the question, how far from the base of the table did it strike the floor, and at what speed? Well, what do we need to do there? We already know that it's moving in the horizontal direction. How fast? Well, it's moving in the horizontal direction at 25.3 meters per second. How fast is it moving in the vertical direction? We can do that over here too, because you see final velocity in the y direction, so we'll have that Vy final, is equal to the initial velocity plus acceleration times time. And now we know the time, so that's going to be 0 plus negative 9.80 times 0.501, almost got rid of my decimal point there, is going to be 4.91 meters per second. Now that is the y component of the final velocity. This is the x component of the final velocity. So if I draw the y component here, arrowhead to endpoint, you add components, and technically that's actually going to be negative 4.91. I dropped my minus sign there. I apologize for that. Meters per second. Let's toss that minus sign in there where it belongs. We use the Pythagorean theorem, and we can get the final velocity when it hits the floor. So rather than moving kind of vertically like I'm showing it here, because it moved way, 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 way out here before landing, it's still moving mostly horizontally. Pythagorean theorem therefore indicates that the final velocity is 25.8 meters per second. I'm assuming at this point that you folks can use the Pythagorean theorem successfully to come up with that answer. So we have answered both questions. The key to the problem is separating the x direction from the y direction and working them independently of each other. The only thing that they both depend on is, once again, time. Once you know the time in one column, immediately transfer it to the other column, and you'll be able to finish the problem. So let's move on to something that's a little bit different from this one. A golf ball is struck so that it leaves the ground at 52 meters per second, that's really fast, at an angle of 30 degrees above horizontal. If the ground is flat, how far away will the ball land, ignoring air effects once again? And this time the air effects we're ignoring are not just air resistance. We also have to ignore any lift effects from the spinning golf ball. Let's take a look at this situation. Here's a golf ball just barely after it's been hit off the tee, and it's moving at an angle of elevation of 30 degrees above the horizontal at an initial velocity of 52 meters per second. How are we going to work this problem? The answer, of course, is the same way we work the other problem. Let's set up an x column and a y column and see what kind of things we know. Now the ball is going to travel on a path like this, and then it's going to land over here someplace. Okay? That distance it travels horizontally is delta x. So I'll put that as our question. And folks, I didn't write this, but of course we're assuming that the x and y directions are the usual ones. Are we finished with the x direction? Well, not quite. You see, it has an initial velocity in the x direction. If you look at our diagram here, we can come across like this, and that is v sub x. It also has some velocity in the y direction. Components are always perpendicular to each other. And this is v sub y initial. Now, why did I call this v sub x and I call this v sub y initial? Well, it has to do with the fact that the x component will not change because there's no horizontal gravity to change it. But the y component will change because there is vertical acceleration. How do we compute these? With a little bit of trigonometry. So v sub x is going to be 52 times the cosine of 30 degrees, whereas v sub y initial is going to be 52 times the sine of 30 degrees. We have quite a bit of information here. So that means that v sub x is equal to 45.03 meters per second. And what else do we know or don't know? Well, once again, we don't know how much time it's going to take. So we're going to need that y column again. And so when we slip over to the y column, let's see what things we know here. Well, let's start with the obvious. It's going to be accelerating, once again, at negative 9.80 meters per second squared. It's going to have a vertical displacement, but how much is its vertical displacement? Well, don't forget what displacement means. It means final position minus initial position. If we're looking at it purely as a vertical motion and ignoring the fact that the ball is moving horizontally, let's say you're standing behind the golfer. So from your perspective, you see the ball going up and coming down. Doesn't it end up at the same height as which it started? It does say the ground is flat after all. So that means its displacement, final position minus initial position in the y direction is, well, this is strange, it's 0, meaning it ends up at the same height as which it started. By the way, if it was on a hill and ended up 5 meters lower than where it started, then delta y would be negative 5. If it was hitting uphill and ended up 10 meters higher than it started, then delta y would be positive 10. It would make the math a little bit more complex, but setting up the problem would be precisely the same. What other things do we know? Well, we know the initial velocity in the y direction is 52 times the sine of 30 degrees. That is 26 meters per second. You can check that stuff on your calculator. And the time is the thing we'd like to figure out. So we set it up the same as we did last time. Since we only have one unknown in the y column and two unknowns in the x column, we work with the y column first. Displacement, which in this case is 0, is initial velocity, 26, times time, plus 1/2 times acceleration, times time squared. Now you might be tempted to solve that quadratic equation with the quadratic formula, and that's a perfectly reasonable way to do it. However, I think this one's easier if you just factor it. The 1/2 times negative 9.8 is of course negative 4.9, but a t can be factored out. So we'd have 0 equals t times 26 minus 4.9t. And that gives us two answers. It tells us for this factor, the t equals 0, and it tells us for this factor, the t equals 5.306 seconds. So what does this mean? Well, it means at two different times the ball had a displacement in the vertical direction of 0. At the beginning, obviously, and at the end when it hit the ground again. Only one of these matters, and that's this one. So we transfer that over to this column. T equals 5.306 seconds. And then we work the problem. First by substituting the variables, and then finishing up. Now this says that the ball is going to travel about 239 meters. And folks, if I could hit a golf shot 239 meters, I'd be pretty dang impressed. But that's not going to happen because I'm old. I'm also not very good. But some people can hit well beyond 239 meters. Okay, again, don't forget that we ignored error effects. But that's how you do a two-dimensional projectile motion problem. Any questions? Ask your physics teacher. See you next time.